Well, good evening, students. Welcome to our Ask Mr. Rich Q&A for Sunday, September 1st. I'm glad that you could make it. And if you're watching the recorded session, I hope it's going to be useful to you tonight. We've got a few students here with us. If you are watching live, you can post questions over in the chat, or you can send me an email to askmrrich@gmail.com. I've got that email up, so I'll be able to see if any questions come through. I'll try to keep my eye on it. What I wanted to cover tonight first, before we get to any of your questions, is I wanted to go over some Desmos tips that you might find interesting. I did talk last week a little bit about Desmos and some other online tools that you can use to be successful in your math classes. Desmos is that tool that you probably know if you've taken the SAT, that it is the online calculator that's in the Blue Book platform that the College Board uses when they test on the SAT and the PSAT. So the more that you know about Desmos and all of its functionality, then you can use it maybe more to your advantage on the actual SAT exam. What I wanted to go over today was some things that you can do statistics-wise in Desmos that you may not know about. Some of the Algebra 2 classes the teachers are requiring you to do what we call linear regression. That is taking some ordered pairs and finding the best fit line that would go through those points. And I want to show you how to do that, and also just do a little bit of statistical analysis using Desmos. So these are some tools that I think are maybe lesser used by students. Most students that get into a statistics class, such as AP stats or probability stats, they're going to rely on their TI-84 to do most of the statistical work. And that's perfectly fine. They should do that because they'll be using that calculator on their test. Won't be using Desmos on the test, I can guarantee you that. But while you're working with numbers, or you're trying to do things a little bit faster maybe than the TI-84 could do them, Desmos is a great option. So I think I'm going to show that to you now. So I'm going to unshare my screen and jump over to show you a few things. What you're looking at here is a list of days that an ice cream store was selling ice cream cones, and it gives the temperature outside and how many ice cream cones they sold on that day. And we're looking to see if there's some sort of an association between the temperature outside and the number of ice cream cones they would sell. Presumably, the hotter it is, maybe the more ice cream that they would sell. When you look at the numbers, yeah, maybe that's about true. I can see that the highest number of ice cream cones was on the day that they were almost the highest temperature of 83. So what I want to do is I want to throw this data into Desmos and make what we call a scatter plot. I want to plot each of these ordered pairs where my x-axis is going to be temperature and my y-axis would be the number of ice cream cones that I sell. What I'm going to do, and this is in Microsoft Excel is where this data is. So I'm going to grab this data and I'm going to copy it. So I'll do a right click, copy. Then I'm going to go over to Desmos. So this is Desmos. Here, as you can see, if you've ever used Desmos, this is what it looks like. You'll recognize it. I'm going to scale it just a bit here. So let's change our scale to go from -10 to 10 on the X, -10 to 10 on the Y. Okay. All right. So there we go. Now, what I'm going to do is I'm going to add a table to Desmos. So a lot of students are familiar with putting in equations and graphing equations in Desmos. But what I'm going to do is I'm going to click this plus sign right here, and I'm going to select table. And it's waiting for me to put in ordered pairs for X and Y. I've already copied to my clipboard on my computer the data for the temperature and ice cream. So I'm just going to hit paste. And it did paste it into a separate table. So I'm going to get rid of that first one. So this is the table of data. So you can see that it has plotted dots for each of those ordered pairs. And it kind of looks like, yeah, there's an upward trend, right? As temperature is increasing, it looks like the Y values, or the number of ice cream cones, is increasing. Now, what I want to do is tell Desmos that I want it to draw the line of best fit. That is the line that would go through the points such that the points are closest to the line. It's what we call in statistics the least square regression line. It's an algorithm that's used to find out the equation of the line, but we don't really want to go into that. We just want to know that we're about to ask Desmos to find the best line that would model those points and pass through the middle of the points. Here's how we're going to do it. I'm going to type in y2. It knew that I wanted to make the subscript 2. Now, I'm not going to hit the equal sign here like we normally would when we're making an equation. I'm going to use a different command. It's called a tilde. And what is a tilde? Well, if I go into the keyboard for Desmos and I don't see the tilde here, so I'm going to hit this ABC to get some more characters. This little squiggle right here is called a tilde. So I'm going to hit that. So now I'm saying y2 tilde. And basically, I'm telling Desmos that I want it to fit a line for y2 based on what I'm about to write on the right-hand side of the tilde. I'm going to put m for slope. I'm going to put x2 plus b. And you can see that what Desmos has added is a blue line that does pass through the middle of those points. And notice that it does give me a value for m and a value for b. That would be my slope and my intercept. So what Desmos is telling me that there's an equation of a line that is the best fit line for this data. And I'm going to go ahead and write the equation here on the screen. So they're saying that y2, which happens to be the number of ice cream cones, is equal to 1.091. We'll round it to 3 decimal places, times x, but x is the temperature. And then the y-intercept is negative 53.358, like that. This equation that I've just written is the equation of that blue line right there. And what would we do with this equation and that blue line? Well, it is what we could use to make predictions for the number of ice cream cones that we would sell if we know the temperature for that day. So if you say, well, I think the temperature is going to be 82 degrees outside, I could estimate or predict the number of ice cream cones by putting in the temperature. We'll say it's going to be exactly 80 degrees outside. And so we could then run that calculation and it would tell me my prediction for the number of ice cream cones. Now, I don't need to do that calculation really, because what I'm going to do in Desmos is I'm going to come over here to where I'm exactly at 80 on the x-axis on that blue line right there. So I can tell you that if I were to do that calculation right there, 1.091 times 80 minus 53.358, it's going to be 33.9. So I'm estimating about 34 ice cream cones I would sell on that day. So that's one of the things that you can do, is make it come up with an equation for a line that would best fit the data. I'll show you something else that can be done as well. If you notice, there's a slight maybe curvature to these points. You might say, well, maybe this fits some sort of a function. Maybe it's something like that. If I thought that that's what it was, I could tell Desmos to come up with an equation for a quadratic as well. I'll show you how I could do that. And I would tell you, if you're watching this and you're taking AP Precalc, you will be doing exactly this kind of thing, but using the TI-84. But it's not a bad idea to use Desmos as a tool, as a backup, and compare them. But what I can do is I can say, well, if I think this data is best modeled by a quadratic, I could say y2, I'll go get the tilde and say ax2 squared plus bx2 plus c. And what it does is it runs an algorithm that will come up with a quadratic in standard form that would best fit the data as a prediction. So you can see that this portion of it, anyways, we wouldn't want to use the whole curve, but from about here up to about here, it does a pretty good job also of making predictions. So I could write that equation by saying y2, which is my predicted ice cream cones, we'll say ice cones, is going to be equal to, the a value is 0.023, so I could say it's 0.023 times the temperature squared. The b value, Desmos says, is a negative 2.15. So we'll get rid of this plus and we'll write it as negative 2.15 times temperature to the first power. And the constant out there, the C, is plus 56.908. Now, if you know a temperature for a given day, you plug it in here, you plug it in here, calculate it all out. It'll make a prediction for the number of ice cream cones that you would sell at that temperature. So anyway, is it only linear equations and quadratics? Of course not. We could have it do exponentials, logarithms. It does all of them. I'll show you one other thing in Desmos that we could do in terms of statistics. And let's see, I'm going to get rid of this. Suppose that we wanted to find the statistics for the number of ice cream cones. Let's just forget about the temperature, and we're just looking at the ice cream cones that we have sold. So let's erase all of that. All right. So some of the commands that we could use right here is I could tell Desmos, I want to know the mean value. Notice when I type the word mean, it's in italics until I get to the end, and it realizes that it knows the key word there is mean. And I'm going to put in parentheses Y2. And it shows me that the mean number of ice cream cones of all of these ice cream cone numbers here is 26.89. Some other statistics, I don't know, the median. I can tell it I want to know the median of Y2. It's 25. The median number of ice cream cones was 25. I'll show you also if you go into the keyboard for Desmos and you go to functions over here, if you don't see what you're looking for on this main keyboard, if you go into functions, there are a lot of different functions. You can see all the statistical functions here, but there's a lot of things down here that it does. Some of them are statistical in nature. It does calculus. So if you're taking Calc AB, there's a lot that you can do here in Desmos that will help you. What I want to show you is these statistics here. If I wanted to find the standard deviation, there's two standard deviation. There's a sample standard deviation and a population standard deviation. I'll go ahead and click that and tell it to find the standard deviation for the number of cones, 12.749. And there's also another pretty cool one here that I believe is just the word stats. So let's get rid of this and we'll do stats and tell it we want all the stats for Y2. And what it does gives us the 5-number summary. These are the numbers that you could use to construct a box plot. So if you're familiar with box plots in your prior algebra classes, or if you're in probability stats or AP stats right now, I'm sure you've been working with box plots. Those would be the numbers for a box plot. But not only will it give me those numbers, I could tell it to create a box plot. I'm going to type the word box plot, and it is one of the commands in the statistical functions. And I want a box plot for Y2. Okay, now the box plot has been graphed down here. It's really flat. I'll zoom in on it and take a look at what it is, but there it is. So that's the box plot. I can change some of the parameters here. I can change the height. I guess could make it a little thicker. Yeah, so I can do that. I can exclude outliers. So if there were some outliers, it would not plot them. Unfortunately, I don't believe Desmos will check for outliers and plot them as points, showing them as outliers. But that right there is a good picture of the box plot. It's showing me that my median value right here is at 22, 24, somewhere between 24 and 26. There's my third quartile, my first quartile, my min, and my max. So it'll make a box plot for you a lot faster than probably you could do it on a TI-84. It'll also make a histogram as well. I don't think it does dot plots. I could be wrong. I'll bet you. Wow. Let's try dot plot for Y2. Yeah. Now, that's not a very interesting dot plot. Let's turn the box plot off because there's no repeats, so it doesn't really show anything stacked. But if you know anything about dot plots, if you've got many points, a dot plot might look good because it'll stack the repeats of certain values on top of each other. You can start to see the shape of your distribution. So that, I think that about does it as far as what I wanted to show you in as far as statistical functions. I could show you on the TI-84 how you would do all of those things as well, because the TI-84 does those things. I could have come in here as if you know how to use your TI-84 statistics wise, if you come in here, I could have put those ice cream cones and temperature in here. It looks like somehow I changed this last one to a 9, but that's the data stored in the TI-84. I can tell it to make a box plot in here by going in here, selecting box plot, telling it that the data is in actually L2, right? We're doing, so I'm going to change this to list 2, which is where my ice cream cone data is stored. I need to turn off, get rid of any graphs that I have in my equation editor. I need to turn the plot on if I want to see it, and then do a zoom 9, and it makes the box plot for me. That's what the TI-84 shows me. That's what Desmos shows me. So it's the same general shape. Now, the TI-84, I think, is a little bit better because what I can do is I can hit trace and I can jump around. It'll show me my 5-number summary as I move around the box plot and hit my arrow button. And it will also calculate any outliers and plot those outliers with a star so I can identify any outlier points. Well, that about does it. So I, at this point, was going to open it up for any questions that you all have. I don't see any in there. Yes, I see a question from, I'm assuming that's going to be from AP Precalc. I sure will do that. I'm going to jump over to a whiteboard. The question is about average rate of change. So let's do that. Thank you for posting that question. I think I can copy and paste it right over here. Share my screen back. Here's the question. This is, can you show how to do the estimate the rate of change of f of x equals x squared minus x at the point of x equals -1? Yes, absolutely. So what we're going to do here is let's take a look at what the average rate of change calculation looks like, or what the formula is. So if you're trying to find the average rate of change between two x values that we call a and b over the interval a to b, what we do is we find f of b, in other words, the y value of our function at the x value of b, minus f of a all over b minus a, like this. And that's what we call average rate of change. Now, this is no different than what you learned back in Algebra 1 and Algebra 2 as y2 minus y1 over x2 minus x1. It's rise over run is what this is. It's just that we're using function notation to represent y2 and y1, and the b and the a are representing the two x values. Anyways, that's what average rate of change is. If I want to get a rate of change estimate at one particular point, here's how I'm going to do it. And I'm going to use my TI-84 for sure. This would be a calculator active problem on your test. I am going to calculate the following values of my function. I'm going to evaluate f of -1. I am going to evaluate f of -1.01, and then f of -1.001. Notice what I'm doing is I'm starting at the x value of interest, and I'm going to get closer. I'm going to pick a second point that gets closer and closer to -1, but not quite to -1. And then I'm going to do f of -1.0001, like this. I'm going to pull up the TI-84 now, show you what we would do. I'm going to go into my equation editor, and I'm going to go ahead and put this equation that we are working with, which is x squared minus x. So I hit x squared minus x. There it is. What I'm going to do now is I'm going to do something that a lot of teachers might not show you. I'm going to use the table feature for this. I'm going to go into second function table set, and I'm going to tell my calculator to start creating a table of x and y values at -1. And I'm going to ignore delta table because I'm going to tell the calculator to ask me for the x values. And now I'm going to hit, and the dependent is going to be auto. So as soon as I hit an x value, it's going to show what the corresponding y value will be in the table. I'm going to do second function table. Sorry, let's get rid of, I'm going to turn these stat plots off. Let's get rid of that. I'm going to look at the table. There it is. I'm going to start with -1. Answer is 2. -1.01, -1.001, and then -1.0001. And I get that. So I'm going to write those values down. 2.0301, was f of negative 1.01, then 2.003, and then 2.0003, like that. What I'm going to do now is I'm going to do an average rate of change calculation between each of these points using this formula. So the first calculation I'm going to do is between f of negative 1 and f of negative 1.01. So I'm going to do f of negative 1 minus f of negative 1.01 all over negative 1 minus negative 1.01, like that. So I'll pull the calculator up, go back to my calculation screen. I'm going to show you a faster way to do this, by the way. I'm showing you how a lot of teachers like want to see the work on a test. But if I go and call alpha F4, no, before I do that, I want to make a fraction. So I hit alpha and this link. If you don't have a color TI-84, you would do alpha F1. I'll show you what I mean. If I clear this, I can also do alpha F1 and it brings up this menu and I hit enter, it'll also make a fraction there. Now what I want to do is I want to call up the y1 function that I just entered in my function. So I'm going to do alpha F4 and enter, and I'm going to say negative 1. So I want it to pass a negative 1 value minus alpha F4, enter, and then negative 1.01, close that off. And then down here, I'm going to do negative 1 minus negative 1.01, enter. So I get an answer of negative 3.01. So the average rate of change between these 2 points is negative 3.01. Now what I'm going to do is I'm going to do it for the next one. So I'm going to scroll up, highlight what I just did there and hit enter and then edit it. So this is going to be, now I'm going to use these 2 points. So I'm going to change this to the second, let's write out the second calculation here. The second calculation is going to be f of negative 1 minus f of negative 1.001 over negative 1 minus negative 1.001. But on my calculator, I don't have to retype the whole thing. What I can do is come up here and say, wait, let's change this to 001. Let's change this to 001. I get negative 3.001. So this one was negative 3.01. This one was negative 3.001. I'll do one more, and I'm going to come up and grab this. So what's happening here is I'm getting a second point that is ever closer to the negative 1. So here it's going to be 0.001, and down here, tacking on another 0.1, and I get negative 3.0001. So the third answer to this takes me out to the third decimal point, negative 3. So I did f of negative 1 minus f of negative 1.0001 all over negative 1 minus negative 1.0001, and I got an answer of negative 3.0001. Out to 3 decimal places, I have an answer of negative 3 as my rate of change at negative 1. I'll just show you one way to like try to make some sense out of what we just did right there. If we plot on Desmos the function that we're working with, x squared minus x, and we do y equals x squared minus x. What we were doing here was we were trying to find it at x equals negative 1. So let's zoom in a bit on this. What we just found is that if you take this function and go to where x is equal to negative 1, trying to get my pen out here. There we go. Right here. We just found out that the rate of change at that point is negative 3. In other words, if you were to draw, and I won't be able to draw this accurately, but if I were to draw a tangent line that would come down here, this is supposed to be a straight line, by the way, that would nick the curve at that one point, its slope would be negative 3. It's what we call the tangent line slope, which is also called the rate of change at x equals negative 1. At x equals negative 1, the slope of that line is -3. And you know what? That kind of makes sense. If you look at my really terrible line right here, you can see the rise over run is approximately -3. It looks like there's a rise of 3 with a run of about 1. Of course, that's scaled differently, but yeah, but you can see it's close. So anyways, I hope that helps. Yeah, so your answer could use, yeah, so you could use 0.999. It doesn't matter. What you could do, I'll show you why the answer key would show that. Because the other way that you could do that is, let me get rid of this drawing there. Okay. Sure. What you could do instead, I'm going to go ahead and erase all this. The other thing, I'm not going to do the whole thing, obviously, but you could say, I'm going to go to the other side of -1. I went to the left side of -1. I could have said, I'm going to go to f of -0.9, or getting a little closer coming in from the right side, -0.99, or f of -0.999, like that. And then when you got out here, your average rate of change calculation that you would use would be f of -0.999 minus, no, sorry, I'm going to use it with the -1. So I would use f of -1 minus f of -0.999 all over -1 minus -0.999, like that. Okay. And I just realized that I think what I might have done here, and now I wish I could go back and unerase because every time that you do these calculations, you don't want to go. I think I did this wrong. I was doing average rate of change between these two numbers. What you're doing is you're still using the -1, but you're using the other point right here. So this would be a really good calculation here as well. F of -1 minus the f of 0.999 over -1 minus 0.99. It'll get you to the same answer. It should. Okay. All right. I see, looks like an AP Calc question. So let's take a look at AP Calculus. And here's the question. What is the limit as x goes to 0 of x over tangent x? So if you're in AP Calculus, you know what this is all about, right? That we're trying to evaluate limits. And the very first thing that we try to do with limits to evaluate a limit is to do what we call direct substitution. We want to plug in the value 0 that we're evaluating the limit at into the function, and we get 0 over tangent of 0. But that's a problem because that gives me 0 over 0, which means it's an indeterminate value. And so we erase all this because it's 0 over 0 does not mean undefined. It doesn't mean infinity. It means nothing. It means we have to do more work to determine what the limit is. So here's what I'm going to do. Let's see if we can do this. There are several ways to get this done. What I'm going to do is I'm going to use one of the trig identities from Precalc. I'm going to replace tangent with sine x over cosine x. Then what I'm going to do is do a keep change flip, right? I'm dividing x by sine x, so I'm going to multiply by cosine over sine. So this really would turn into the limit as x goes to 0 of x times cosine x over sine x. Next, what I'm going to do is I'm going to use properties of limits, and I'm going to break this limit apart. And I'm going to do this. I'm going to take this as the limit as x goes to 0 of x over sine x times the limit as x goes to 0 of cosine x. You can see that x over sine x times cosine x does give me this original fraction, but the properties of limits say that I can split my limit parts up that are being multiplied. I can split it into two separate limits. Now you may say, well, why would you want to do this? Or how was I supposed to know that would be my next step? Well, because we are looking for something that looks like x over sine x or sine x over x, because one of the limits that your teacher has shown you, I'm sure by this point, is a special limit that says the limit as x goes to 0 of sine times ax over ax is equal to 1. I almost have that in this limit. It's just that it's flipped. So I'm going to go to the next step, okay? Here's what I'm going to do. I'm going to change this to the limit as x goes to 0 of sine x over x raised to the -1 power. And of course, I still have this limit over here. And I do know what this limit is, by the way, but I'll bring it along until I'm ready to evaluate it at the end. There's another property of limits. I could show them to you, but I'm just going to I could show you the whole list of properties, but hopefully your teacher has shown you a resource that shows all the different ways you can manipulate limits to evaluate a limit. One of the properties is that if I am taking the limit of something raised to a power, what I can do is take the power to the complete outside of the limit. So I am now going to take that -1, instead of it being applied to the sine x over x, I'm going to bring it out here. And then this would be the limit as x goes to 0 of cosine x. But I know what this value is right here. We've already established that that limit is equal to the number 1. So this is 1 raised to the -1, which of course is just 1. And if you do direct substitution here, cosine of 0 is 1. So my limit here is the number 1. And that is the answer to that question. Now, this is where Desmos comes in, right? If you're like, you know what, I'm not sure I buy that. I'm not sure that the limit of the original thing that they asked me is equal to 1. Well, I'm going to go graph this function and see what its limit is graphically. I'll go over and graph x over tangent of x right here. Well, it's a weird looking function, right? We had no idea what it was going to look like. Apparently, that's what it looks like. But if we're interested in where x approaches 0. So you can see that both from the right-hand side of 0, it's approaching a y value of 1. And I'll bet you there's a hole right there. That's why we got 0 over 0. So you can see that the function does not exist at x equals 0. The function's undefined at x equals 0. However, the limit does exist because as you come in from both the right-hand side at 0, from the right of 0, and as you come in from the left of 0, the closer and closer you get to the y value of 1. And that's why my limit is equal to the number 1. All right. So I hope that helps. It's also something you could evaluate numerically on your TI-84. I'll show you that as well. If I decide to use my TI-84 to evaluate that limit, I could come over here and make a fraction and call it the original function x over tan of x. Anytime that you're dealing with trig functions in your equation editor, you have to make sure you are in radians mode or game over. You won't make any sense. You will not get any right answers. So I've got that in there. Now I'm going to use the table feature. What I'm going to do is I'm going to tell the table to start evaluating my function at x equals 0 and to go up in really small increments. I'm going to do 0.01. And I'm going to tell it to autofill the table for both the x and the y values. Now I'm going to go look at the table. You can see that I do get an error at 0 because the function doesn't exist at 0. But look at both the right side of 0 at 0.01 and the left side, it rounds to an answer of 1. So that confirms numerically that the limit as x approaches 0 of that function is the number 1. Any other questions out there? Now, as far as the question that I was asked, I do want to go back to this pre-calc because the more that I looked at it, the more that I realized that I really think I didn't do this the right way when I was showing you this. I'm going to go show you, I'm going to jump right to evaluating the average rate of, the rate of change at -1, which is what our question was, but using this super duper close value to -1 of -0.99. So basically what I'm going to say is this, is that the rate of change of my f of x at x equals -1 is approximately equal to f of -1 minus f of -0.999 over -1 minus -0.999. Now, again, I could have used -1.0001 here. Doesn't really matter. I'm going to get the same result. I just need to pick a number that is super close to the value at which I'm trying to evaluate the rate of change. Going back to the TI-84, we will change this back to what we were working on, which was x squared minus x. There it is. We'll go back to the calculation screen. Let's make ourselves our fraction. We will call up our alpha f4y1 at -1 minus, call up the function again, at -0.999 all over -1 minus -0.999. Close it off. We get an answer of -2.999. And the closer that I pick a value to -1, so if I carry this out to 4 nines, 0.9999, or 5 nines, the closer I'm going to get to -3 for the rate of change, because the rate of change is -3, but we need calculus to get the exact value. That's why we're using an average rate of change calculation, but the 2 points we're using are really super close together to one another. So it gives us a very good estimate. And the estimate gets better and better the closer that second point that we choose is to the point where we're trying to evaluate the rate of change. Any other questions out there? I think the two students that I have here are pre-calc and calc. So let me see what I had. We've got about 10 minutes left. I might be able to get a few problems in. All right, I think I want to take a look at this problem here. This comes from Unit 1 of AP Pre-Calc, and I think this is section or lesson 1.6. Determine if the following function is even, odd, or neither. This really is something that you would have learned back in Algebra 2, how to determine even, odd functions. Well, first off, I know that the answer to this is going to be neither, because if it's a polynomial, and it is, and my exponents on the variables are a mixture of even and odd numbers, it's going to be neither, right? I have an x to the 2 and an x to the 1, so it's neither even nor odd. Now, how would I show that it's neither? Well, the first thing I'm going to do is I'm going to check to see if it's an even function. Even functions are functions for which the following is true, that the function itself is equal to f of -x. So I'm going to calculate f of -x and see if it gives me f of x. So I replace all of the x's with a -x, and I'm going to get that. Well, when I replace this x with a -x and then I square it, you know that when you raise a negative to an even power, it's going to turn it back to a positive. So this is going to be x squared, excuse me, and this is going to be plus 4x minus 3. And you can see that this result that I got for f of -x is not the same thing as f of x right here. And I'm sorry, this is supposed to be a -x right here. 4 times -x, which makes that -4x. So the difference is that the original function was a plus 4x, but the f of -x has a -4x. So I can come to this result and say f of x is not even because f of x is not the same as f of -x. But now I can check for odd. And the requirement for odd is that f of -x is supposed to be negative f of x. Well, for this check, I've already done. Oh, I see the question that you had. Does it mean that -3.001 and -2.99 are both correct? No, I'm going to say this way. So her question is here, or his question is that -3.001. What you have to do, I'm going to go back and answer this question here on the pre-calc, this one here, that what you want to do is you want to keep doing this until you get to the third decimal place. So in other words, if you keep going, and here's your two results. If you got a result of -3.0001 and you got a result of -2.999, both of those round to -3.000. So I would say that you want to get your answer out to that third decimal place. And so the right answer really would be a -3.000. So I hope that helps. back to this. The odd check is to show that f of negative x is equal to negative f of x. Well, we already know what f of negative x is. So the only thing that we need to show is what is negative f of x. Well, negative f of x means to multiply the f of x by a -1, changing all of the terms. So negative f of x is going to be negative x squared minus 4x plus 3. And that is obviously not the same as f of negative x, which was this result here. So I can say that f of x is not odd because f of negative x is not equal to negative f of x. And so therefore, my conclusion, my final answer here, therefore f of x is neither odd nor even. There we go. I'm going to do another calculus problem, and I think we've got time to do this one. I want to show you the transition in calculus that we make from average rate of change to rate of change. If we've got some function f of x and we pick a point A, and we want to get the rate of change at point A, the question that we were just working on, where I was picking a point very close to the -1 that we were trying to find the rate of change at. This kind of follows on that, because what I'm going to do is I'm going to say, here's the point A where I'm trying to find the rate of change. I'm going to pick point that is h units away. In other words, this point is really not h, but it's a plus h, meaning this distance between these 2 points is h. So this x value is f of a, excuse me, this y value is f of a. This y value is f of a plus h. The average rate of change between those 2 points would be, f of a plus h minus f of a all over a plus h, right? That x value, a plus h, because that distance is h. So it would be a plus h minus a, but a plus h minus a is just a. So really the average rate of change calculation here, according to this picture, is that right there. But this is where limits come in, because if I want to get the rate of change exactly at point A, I'm going to take this fraction and let h approach 0. So here's what I'm going to do. I've got the function x squared, and I'm going to use this, what we call the difference quotient, to find the slope of the curve at x equals 3, at x equals 3. So I want the rate of change at x equals 3. What I'm going to do is I'm going to take the limit as h goes to 0 of f of a plus h. Well, f of a plus h would be stick a plus h in for x. Oh, and what's my value of a? My value of a is going to be 3, because that's the point right here, is going to be 3 in my problem. So I'm going to say that I'm going to put 3 plus h in for x. It would become 3 plus h squared minus f of 3, which is a 9, all over h. Now, I can't put 0 in. I can't do direct substitution at this point, because if you put 0 in for h, I'm going to get 0 over 0, and that's indeterminate. So I have to keep working this out. I'm going to expand the 3 plus h squared. That's going to be 9 plus 6h plus h squared minus 9 over h. 9 minus 9 cancels. We're getting closer now. The limit as h goes to 0 of 6h plus h squared all over h. Notice in the top, I have a common factor of h. This becomes 6 plus h over h. Notice the h's right there cancel. Now through direct substitution, I get an answer of 6. I got an exact value of 6 right there. So I can say that for this function, f of x equals x squared, if you go over to where x is equal to 3, the slope of the tangent line, also known as the rate of change at that point of x equals 3, that tangent line has a slope of 6 right there. That's how we do it. That is the jump that we make from pre-calc to calc. This is what we did over here, is we were using average rate of change for 2 values that were really super close to each other. In calculus, we let those 2 points actually come all the way together by taking the limit as h goes to 0, and we get immediately straight to the correct value. If we were doing this on the way that I was doing with average rate of change, we would have got answers like 5.999 and 6.0001. But the closer that I bring those points together, the closer the answer on an average rate of change would be to 6. In calculus, though, we go straight to the result, which is 6. All right, students. Well, I hope that was helpful. I do appreciate you checking in. Join me next week. I'll be here again at 8 o'clock on Sunday night, and we'll tackle it again. I hope you all have a great week, and talk to you soon.